Greetings from Microlab Northwest. The light microscope is a key to understanding our environment. The particles that we see, that we collect off surfaces in our environment, tell us about the things that we've been exposed to, how much we've been exposed to, and what might be causing health complaints or other issues. We've looked at how we might use the light microscope in terms of illumination systems. We've looked at how important reflected dark field illumination is, and we have an attachment to make any microscope capable of reflected dark field illumination. We've also looked at the importance of oblique illumination, dark field illumination, bright field illumination. Later, we'll look at how we might even use polarized light illumination. But for now, we thought we might take a look at one group of materials that we may find in our environment if there is a wildfire nearby. There are literally tens to hundreds of thousands of samples every year run by laboratories trying to establish the extent of exposure to smoke from wildfire. That's typically called soot, char, and ash analysis. We'll take a look at these three types of materials and see how we analyze them and what they tell you about the environment. Can you really tell the difference between a wildfire smoke event and that you might have from a house fire or an industrial fire or a fire in your backyard or fireplace? And the fact is, yes, you can very easily. But we'll take a look at that. We'd like to start by taking the soot, char, and ash family of materials, and we'll look at ash as a beginning. In any wildfire event, any wildfire exposure, ash is a significant part of the total material that you might be exposed to. Ash is the result of complete combustion. All of the carbon and hydrogen has been removed. What you're left with are the inorganic materials that are part of plants, the things that burned during the wildfire. If you go to an area that has experienced a wildfire, let's take a forest. When you look at that forest after the fire, the trees are still there. All the leaves are gone, the twigs are gone, and the bark is significantly charred. But most of the wood is still there. As a matter of fact, in many of these events, they come in after the fire and harvest the wood. So what we're looking for in a wildfire event from a forest fire is the debris that comes from the needles of the tree, the leaves of the tree, twigs, and bark of the tree. In a wildfire event, you're not just being exposed to one plant, there are many plants. And we'll see some examples of that. One of the major parts of the ash during these fires are what are called phytoliths. Phytoliths are little stones that are actually made by the plant that serve a number of functions. One family of phytoliths are the silica phytoliths. These are made predominantly of silicon dioxide that has been hydrated, so it's actually an opalescent silica. These particles take very characteristic shapes, and these shapes are easily identified, as you can see here We have a number of silica phytoliths from grasses. You have the characteristic barbell shapes. You have little cubic type shapes, rectangular shapes. You have elongated fiber shapes. You have denticulated shapes. Denticulated shapes, that means they have teeth. You can see along the edge of these grass phytoliths, the sharp edges, the teeth that form on the surface leaves of grass. These are protection for the grass. You also have elongated fibers. They're trisomes, is their technical name, but these are the hairs that grow off the surface of grasses and many leaves. These silica phytoliths survive the fire. Many of them are difficult to tell from the unfired phytoliths. In the middle North American continent, up to 5% of the soil is made up of phytoliths from grasses that have decayed and dropped these phytoliths into the soil. Trees also have silica phytoliths, but they're more complex in shape. And we can take a look at some of those too. One example here, you can see very irregular shape. Another form of phytolith is the calcium oxalate phytoliths. The calcium oxalate phytoliths go through a number of thermal transitions that can actually tell you what temperature it was exposed to prior to being released by the leaves or the bark of the tree. These phytoliths have a number of intricate shapes that are under some genetic control. So families of plants have similar shapes of calcium oxalate phytoliths. These calcium oxalate phytoliths go through a number of transitions chemically that change their optical appearance, but the shape stays constant. The shape of a calcium oxalate phytolith fresh out of a tree, a leaf or a bark, has a characteristic shape for that type of tree and that particular part of the tree. When these are exposed to higher temperature, the shape stays identical, but the optical properties change. They become light scattering. The importance there again of reflected dark field illumination. When you look at a fresh calcium oxalate phytolith, it's a nice clear crystal. Light passes through it easily. It scatters very little light. So with reflected dark field illumination, you only see the edge. The crystal itself stays clear. If it's been exposed to temperature, it becomes light scattering. When you turn on the dark field reflected light system, the particle lights up like a beacon. Very easy to see. As a matter of fact, when you're looking for fire debris, using reflected dark field illumination is one of the best ways to quickly identify the presence of these phytoliths and of other forms of ash. They light up bright against a dark background. A real advantage to having reflected dark field illumination. Another form of ash is the residue of the inorganic compounds that are in cell walls and cell structures. These are extremely fragile. They break down very easily. But if you've used tape lifts to collect the samples off surfaces, then you may still see the cell structure in the residue that's left behind, this ash particle. These ash particles are also highly reflective. But if you look at them with just reflected dark field illumination, they all scatter. They look white. You see very little information. But with transmitted light, you can see quite often cell walls. The reason for that is that where the walls were, there's a thicker layer of scattering material. So you're not just scattering light off the surface. You've now lost a lot of light because of the scattering of the beam that's trying to come through the ash particle. So these particles will show cell structure quite often. If you took a wipe sample instead of a tape lift, that's all destroyed. They are simply gone. Not only have you destroyed the structure of these very fragile particles, but you have also dissolved part of the materials that make up this structure. Many of the potassium salts that form this kind of ash are soluble in water or in alcohol. So if you use alcohol or water moistened wipes to take your sample, many of those materials have simply gone into solution and are gone. If you use a microvac, the microvac also will destroy these extremely fragile particles. There are many examples of the fragile structure of ash particles. As you can see, many of them are extremely fine, made up of very weakly attached individual particles. The way, the pattern of their attachment is the cell structure. Anything that applies a force to that surface will destroy that structure. Tape lifts work because they actually bond the material in the adhesive on the tape. So ash coming from these plants, we can understand, we can identify, but what are some of the characteristics that tell us, for instance, that the silica phytoliths have been exposed to flame? One of the things is they are quite often marked with soot or with what's called a carbon mirror, where the carbon actually has plated out on some of the materials, making it appear darker. If the fire got hot enough for long enough, all of the carbon is gone. But as I mentioned, the silica phytoliths often have water of hydration mixed in with their structure. As a result, when they reach a high temperature, the water begins to come out, and it makes the particle look frothy. These frothy particles, with reflected dark field illumination, are bright. Again, they are light scattering. That doesn't occur unless they've been exposed to high temperature. So there are a number of things that we can see in ash. Ash, as we said, is a very significant part of the total emissions coming from wildfires. They are easily identifiable. The phytoliths, silica, or calcium oxalate give you some history of the fire, how hot it was, what plants were burning, what parts of the plants were burning. That's all recorded in these ash particles. The ash particles that are not calcium oxalate or silica, the potassium-rich components, are extremely fragile. They are very aerodynamic, carried for long distances in the plume. can get into buildings from the outside and can be identified in terms of the cell structure that's there. All of these things are important. They are critical to the identification of a wildfire plume. So this is a kind of the story of how we start identifying wildfire debris in a home. The next part, we'll discuss char. But for now, that's enough. See you next time. As a postscript, we are making available a number of standard slides. We're looking at grasses, trees, bark, leaves that have been ashed, as well as some that have not been ashed, so that you can see the structure of these phytoliths prior to exposure to fire and then after exposure to fire. We'll also have some standard slides showing what these things look like when you pick them up off surfaces in a home that has been exposed to wildfire. With the right illumination, you can easily identify the wildfire debris among all of the other materials that were on the surfaces in those homes. So those are some things that we're offering along with the epi-illuminator. We'll have more on that in a later video.